Welcome into the arena. My name's Allyson Klein. I am so excited for this episode. We've got Robert Blum, Senior Vice President of Sales and Marketing from Lightwave Logic with us. Welcome to the program, Robert.
Thank you, Allyson. Good to see you again.
I wanted to call this episode Prophecy Foretold, Prophecy Delivered, but we'll get to why I want to tell it that in our conversation. Why don't you just go ahead and introduce yourself? You're one of the industry's leading expert on optics. I've known you for a long time, and you've always been the guy that I've turned to for insight about optics. And you recently moved into a really interesting role at Lightwave Logic. Tell us about the company, tell us about your background, and why you're here today.
Sure, Allyson. Thanks for having me, of course. Integrated photonics or optics has really been key to data center interconnects and data center connectivity for the past, I want to say 15 or so years, right? And it's all about transporting large amounts of data, what used to be between servers and now, of course, between tens of thousands of GPUs, right? And so you need these optical transceivers, you need these optical communication links, and it has become a really big market. I mean, if you look at just the optical transceivers, it's about a $20 billion market today, and it's growing to like $40 billion the market. And the majority is really on silicon photonics. And so what we make at Lightwave Logic are electro-optic polymers, and they work together with the silicon photonics, and they enable the next transition to the next generation higher data rates in optical networking and AI, right? So we're really enabling high-speed modulators. And so these are hundreds of millions of modulators that you need in those data centers and AI clusters. And so it's a huge market. It's a multi-billion-dollar SAM, even in the 2028 timeframe. So I'm very excited about this opportunity here.
Now, I talked about prophecies earlier. About a decade ago, we recorded a podcast together, and I just listened to it recently. It was in another chapter of each of our careers. In that episode, we were talking about the migration of 25 gig Ethernet to 100 gig optical networks. And you predicted something really interesting. You said that the bandwidth demand would double every couple of years moving forward, which was a ridiculously bold claim at the time. But you were right. What are the trends that did you see then, and how has that played out on the demand curve now?
Mm-hmm. Sure. So back then in 2016, the SerDes speed was moving from 10 gig to 25 gig, right? So the Ethernet speeds and the NICs that could connect the servers, the network interface cards or controllers, they were going from 10 gig to 25 gig. And what that meant for the optics is that the optics that aggregates essentially 4 lanes of 10 gig or 25 gig was moving from 40G to 100G, so 100 gigabits per second optical transceivers, right? But if you look at sort of the Ethernet speed, and there's a long history of Ethernet speed, evolution, it really used to double every 4 years roughly, right? So if you look at 1 to 2.5 gig to 10 gig to then 40 to 25 gig and so on, it's really been doubling every 4 years. But the problem, even back then in 2016, was that the racks of servers were really bottlenecked by networking. So you couldn't really get enough data to and from the compute servers. So the networking, the top of the rack switches that were aggregating all the traffic to and from the servers were already bottlenecked back then. And so there was this huge need to actually increase the networking bandwidth back then, right? And so the only way to do that is really to go faster with those speeds. And so you can increase the speeds or you can aggregate more channels. And so, that's why it had to move essentially from sort of doubling every 4 years to a doubling every 2 years, give or take, right?
Now let's shift into today. We are seeing a transition again to 400 gig. Why is this a critical moment for optics and for polymer technology in particular?
Right. So actually, just to kind of calibrate on that, so what's being deployed now is actually 200 gig per lane transceivers. So the electrical lane, what I just mentioned, we talked about back at about 225 gig, the electrical lanes are now at 200 gig, and the optical transceivers are at 1.6 terabit. So you have 1.6 T transceivers. So if you compare that to the 100 gig transceivers that we had 8 or 9 years ago, that's 16 times the speed, right?
Mm-hmm.
So it has doubled essentially 4 times, which is what we had thought it would, right? But it's still not enough, obviously, right? And so now customers are really wondering, with electrical SerDes now being developed for 400 gig, how do you get the optics also to 400 gig? Because you always want to have the electrical bandwidth matched to the optical bandwidth, right? And
Mm-hmm.
so, and even at 200 gig today per lane, silicon photonics or other technologies have a lot of challenges, right?
Mm-hmm.
And so they're struggling with how do I get to 400 gig per lane on the optical side, and so that's where people come to us and say, well, can you help us? Polymers are the fastest material out there. Can you augment the silicon photonics with polymers to enable 400 gig per lane speeds, right? So again, it's all about the networking bottlenecks and being able to go faster, because you want to match the optical speed with the electrical speed, and you don't want to be have to now suddenly downgrade and go slower on the optical side if the electrical is moving to 400 gig.
So time out, because we've been talking about this thing called polymers, electro-optic polymers in particular. I know
Right.
you've got your PhD in this field, so you're the guy to ask. How are they used today, and what is an electro-optic polymer?
Right. So I did actually my PhD back in the 1990s on electro-optic polymers for high-speed modulators and also for optical switching. There were some applications in that field as well. And Electro-optic polymers are really this interesting material. Basically, you have these molecules that are dipolar, and when you apply an electric field, or when you apply electric voltage across the material, the refractive index changes. And what's important is that the refractive index changes essentially is instantaneous, right? So you
Mm-hmm.
don't have to move any charge carriers around. It's basically just an electron cloud that reacts to the electric field. So um, they're very, very fast, and they have a very large electro-optic coefficient, which means that the refractive index change that you get for an applied field or voltage is very large, right? And so what that means is you can make very compact, small modulators, and you need very low, you can get away with very low drive voltages, basically, right? And so, at Lightwave Logic, we have developed these prokinamine chromophores that that are part of the polymers, and you can deposit them using standard spin coating in semiconductor fabs, right? So that's a nice thing. It's nothing special. It's just like a photoresist in the fab that you can deposit at the wafer level.
Now, fun fact, my first In the Arena podcast was about polymers, and it was about polymers in the OLED industry. I remember from that episode that there was a ton of discussion that polymers were never going to be ready for the OLED market. Can you tell us what's happened in that market over the past few years?
Right, right. Well, in the OLED market in particular, obviously today, organic LEDs are everywhere,
Mm-hmm.
as you know, right? So the smartphone, which I put somewhere here on my table, has OLEDs. The TV, most TVs, high-end TVs have OLEDs. Smartwatches have OLEDs, right? And key for that was really a process called encapsulation, right? You need to protect the material from oxygen and also water humidity, right? And with that, those materials can last essentially indefinitely, right? And there's two things that are interesting on that topic. Is one, basically for us, and maybe we're going to talk about that later. It's essentially a similar situation where we need to encapsulate the material to make it reliable, right? And the other thing is that the industry has really developed standard semiconductor equipment, such as atomic layer deposition, that's now available in the foundries. So both wafer level and at the panel level, right? And so that's really a huge plus. But I do want to say that overall polymers in general are or can be very reliable. I mean, they're used today in telecom datacom components for fiber attach, for example. You have optical quality adhesives, and in telecom components they also have been used uh, for a couple of decades actually in high reliability telecommunications equipment. Right?
Now you kind of prophesized the next question, which is, within the OLED market, there was a lot of question about polymers. Same views apply to polymers and optics. Why is this moment different for the optics evolution for integration of polymers?
Right. Yeah. So I mean, since back in the 1990s when I did my PhD, right, has been 2 to 3 decades of research, and we really have a very different fundamental understanding of polymers and what it takes to make these chromophores reliable at a molecular level, right? So there's a few things that you need to do, and one is obviously you need to make sure that those materials can operate at high temperatures. I mean, we need to be at like 85 degrees centigrade in some of those modules. So they need to be inherently reliable. But then also we need to obviously encapsulate them. We have to protect them from oxygen and from humidity, and we understand those failure modes really well. Um, if you design the material the right way and you encapsulate it, right, then it is reliable, and we have data for that now. And then the other point is that there's really no good alternative to get to 400 G per lane, as I mentioned earlier, right? So um, the time is right in a way, and then on top of that, in particular with AI performance is really bottlenecked by networking, right? And so polymers are solving a true high value problem today. It's not just like an academic endeavor. Oh, we can go to higher speed. We're actually solving a real networking bottleneck in AI clusters and also in the wider data center space.
Now, let's talk about the pain point everybody's facing in this space, power.
Mm-hmm.
One question that I have in my mind is, do polymers offer a sustainability advantage compared to traditional materials used in optics?
Yeah, that's it's actually a funny question. You sound a little bit like my former CEO. A lot of it is around sustainable differentiation, right? And so if I look at the advantage today, um, the advantage of polymer modulators is really the very low power dissipation. So we don't need a bias voltage to operate the modulator, and the voltage to drive the modulator, right, is very low. So that means the overall power dissipation that you get is much lower than other technologies, right? And that's actually why we're seeing adoption and market traction already today at 200 G per lane, because people want to make products with better performance and lower power dissipation. Um, and um, and because of the high electro-optic coefficient, we're able to make the devices much smaller. So
Mm-hmm.
so space is super important in these packages. The smaller you can make it, um, the better, and the more bandwidth can you put in there. There's another term, shoreline bandwidth density. How many terabits per millimeter can you uh, get in and out of a GPU or a switch, for example? So, on all these metrics, we're basically, much better than other technologies. And in terms of the sustainability, because the polymers have no inherent cap or limitations on the bandwidth, we can go much further, right? I mean, we can go well beyond 400 gig. In fact, one of our customers has demonstrated a terabit of data transmission already. So there's no limit to the technology, which is also important, right? So obviously we're working with customers now on 200G per lane and 400G per lane, but there's a roadmap and capability to go beyond that, right? So that's really important in terms of sustainability.
Now, you and I have both had experiences where technology visions are amazing, but until you're production ready, they're just that, they're a vision. So I have to ask the question, are you materials production ready? And where are you in working with the ecosystem to get ready for mass market introduction?
Mhm. Yeah, so we have a PDK, a process design kit, to deposit and also encapsulate the polymer, right? So we're working with our customers, and maybe more importantly, even with the silicon photonics foundries, to enable that PDK as part of their standard photonics silicon photonics foundry PDK, right? And that's really key for to be compatible to. Um, that's really key for high volume manufacturing, is to be compatible and be part of the standard silicon photonics CMOS foundry flow. Right?
Now, Lightwave Logic has been around for a long time, and some of us who are listening might remember Lightwave Logic as a full product delivery engine. What's shifted in the company, and why is that an important shift in terms of market traction?
Mm-hmm. Right, that's an important point. Yeah, so we used to make devices, modulators and integrated chips, but our strength is really in the electro-optic polymer, in the material design, synthesis, and also in the encapsulation process. So by shifting to a model where we're providing the material to the transceiver manufacturers and system houses, AI companies, it really allows us to address the entire market. Right? We can co-innovate with our customers and foundry partners, and really support or enable the entire ecosystem, right? With our materials. So we're providing material, licensing our IP, provide reference designs based on our learnings from the past, but it's really it's a very different situation where we're basically enabling the entire market, as opposed to, say, competing with our customers.
Now let's talk adoption. What kind of customer traction are you seeing now, and where are you on the journey from evaluation to actual design wins?
Yeah, we're seeing very broad traction from transceiver companies making transceivers like the 1.6T transceivers that I mentioned earlier, to AI companies who make entire AI systems, to the hyperscalers. We're in the design win cycle with several customers, right? And what is interesting, actually, what surprised me is that they don't wait for 400G. They're starting now with 200G already, because they see value in that, right? I mean, it's interesting to see, because it seems like some of the existing legacy materials, like just silicon photonics or indium phosphide, they're already struggling with 200G.
Sure.
So customers are designing products based on with polymers based on that, and obviously for 400G, there is a real use, very large urgency to move to polymers, right? And again, it's not going to stop at 400G, as I mentioned earlier.
This is complex technology. This is a complex industry in terms of the market transitions going on and the full value chain of delivery of solutions. What do you want the industry, and I guess I'd say investors too, to understand about Lightwave Logic's differentiation in this space?
Yeah. I mean, I believe we have an unparalleled expertise in developing reliable, high-speed electro-optic polymers, right? So the prokinamine polymers we have are really ready for prime time. We also understand the ecosystem and the customer and foundry space really well, and the need for high-speed networking. I think the other thing is that really we have a business model that allows us really to enable the ecosystem without competing with customers, as I mentioned. So that allows us really to continue to innovate and enable these next generation transitions in optical networking.
Now, one thing I learned, and I think this question will resonate with you, Robert. One thing I learned at Intel is that semiconductor engineers don't necessarily speak optics fluently. So how are you bridging the understanding gap with silicon-centric organizations?
Right. Well, I mean, it's interesting. When we first spoke back in 2016, I think silicon photonics was new, up and coming, and the fact is it has come a long way since then. It's in only 8 or 9 years. I mean, all major CMOS foundries have silicon photonics now, including TSMC, as is well known. So it has sort of become much more mainstream, also because of the need for these optical interconnects, I would say. The other thing is actually that because of the packaging, so packaging of photonics optical chips and electronics is much more tightly integrated, right? So
Mm-hmm.
in
Yeah.
a way, we can think of photonics or silicon photonics now as just another chiplet in a multi-chip module, right? So a lot of these advanced packages that have many different, electronic logic CMOS chiplets, they now also are looking at, okay, how do I get another photonics chiplet in there, right? And I think the other point is, yeah, that silicon photonics is just really now part of a standard CMOS flow. And what's nice for us on the polymer side is that obviously we can just be part of that standard CMOS flow as well, right? Because we're not introducing any exotic materials. Our material is just like a standard photoresist that you see in any CMOS fab.
Now let's talk competition. We did a little homework for this episode, and there are some competitors in this space, so I wanted to ask you about them. How does Lightwave Logic stack up against other electro-optic materials like TFLN or indium phosphide?
Mm-hmm. So one of the benefits of electro-optic polymers is that they have a very low dielectric constant. And what that means is that you're actually able to match the optical wave and the electrical wave much better, which means you can actually get fast modulators. It's much easier to design a modulator with a polymer where the optical and electrical waves are matched. Um, and electro-optic polymers have the highest EO coefficient out there really in terms of practical materials. We're about 10 times the EO coefficient of lithium niobate. So that means we can have a much lower drive voltage and therefore much lower power consumption as well, right? Which allows us to get to very compact modulators and to a very high density. Actually, you asked about sort of the sustainable differentiation. Things are only going to get more compact over time, right? If you look at co-packaged optics and you're trying to integrate optics with, the GPU right next to the GPU, you need to make very compact modulators, very compact chips, right? So that's a big differentiation for us. And we can make very, very small, very compact modulators. And we're fundamentally easy to integrate into a silicon photonics foundry flow. I think I mentioned that already 3 times now, but it's really a key point that it's easy to integrate.
Yeah, that's awesome. My final 2 questions are about prophecies. You're so good at them, so I thought we'd introduce them this time too. Let's just say that you're successful in delivering EO polymers to AI data centers. Beyond that, do you see opportunities where in quantum computing, telecom, other markets? What does the landscape look like?
Right. Yeah, so obviously the focus today is very much on AI. I mean, I'm really trying to focus the team and say, well, this is obviously the biggest opportunity, especially in the near term. We do see demand for telecom applications in a way that's actually somewhat easier from a device perspective, and it's actually a good opportunity. There's some higher value, but obviously the volume is much smaller. We do see opportunities in the quantum space, as you mentioned, in meta surfaces, free space optics, sensing. It's actually funny. I'm very familiar with those markets actually from my past work,
Mm-hmm.
and so there are quite a few opportunities, right? And it's actually one of the things with us providing the material or licensing the material. It makes it easy in a way to enter that segment because we can just provide the material to people working on devices or products in that space without having to go and design, say, a meta surface, for example, right? But the way I think about it is, once we have the material platform established in the leading silicon photonics foundries, then it's easy for some of those designers that are working on these new markets, like in quantum computing, for example, to go and design a chip with our polymers, right? So the first step is really focus on AI, but I would say, starting next year, I think we'll have more in-depth discussions with some of our customers in that space. Yeah.
So, final question. As we look at that AI data center market, which is incredibly vast and large market, even before we get to what's beyond, what milestones will tell you that the market in the world is finally ready for polymers.
Mhm. Yeah, so we're focusing on supporting customers in the AI space now, right? We
Mm-hmm.
expect to have three to five customers at an advanced stage of the design win cycle, by the end of this year. And then it's really about making steady progress, with those designs, and product qualifications that our customers have to do. Um, and the goal is really to be in volume production in 2027, right? And as I said earlier, there's really no better material, in my opinion, to enable 400G per lane optical networking. Uh,
Mm-hmm.
it also has a credible roadmap actually beyond that, right? And so, if we go back to what you said earlier, we need this 2x per year increase in bandwidth, right? And that's not going to stop with 400G. So
No,
the innovation is just going to continue.
that's incredible. Well, Robert, every time I talk to you, I learn something new. We'd love to have you back on the program whenever you want to come back. I'm sure that we piqued interest from folks in our audience. Where can folks connect with you and learn more about Lightwave Logics solutions?
Mhm. Yeah, the easiest place is obviously our website. So it's lightwavelogic.com.
Mm-hmm. Awesome. Well, thank you so much for your time today. It was a real pleasure.
Thank you, Allyson.